Hi everyone, I'm Jonathan from Imperial and ConsenSys Health. I work with. And first of all, I'd like to say I really enjoyed the last panel. That was all you guys, or what you guys said was just music to my ears. Both the panelists and the amazing questions from the audience. You've set the stage for this talk. I've heard many things. I've heard blockchain was not a silver bullet, and that's clearly what we're advocating here. I think if we're in this room, we're all convinced that blockchain is an amazing piece of technology, but it's definitely not a silver bullet. I've heard for the necessity of auditing what we're doing with data, which is extremely important as well, especially in the context of AI. I'm going to use the AI prism to advocate the necessity for the technologies we're presenting today. And I'd like to first of all start with a discussion that happened on Twitter a few months ago. You've probably seen it. I guess you know these two guys over here. So we've got Elon Musk. It's not the first tweet of the series actually. He started by just tweeting Ethereum, just to tease the audience. And what happened afterwards was that people was wondering why was Elon Musk talking about Ethereum? Was he kind of like shilling Ethereum in a way? And then he tweeted, just kidding. So I think Vitalik didn't like it very well. And they engaged in a conversation where Elon Musk ended up asking, but what actually should be developed on Ethereum? And out of the top picks of Vitalik, I think one that was very important in this conversation was, well, we could use Ethereum to build markets for personal data for privacy preserving machine learning. So you pay me X, and I'll let you execute a function Y on my data in what we call a homomorphic way, so in a fully encrypted way, which is basically what the panel has been describing as an ideal solution. So if we put that into context, this is the kind of marketplaces that we could envision with these technologies. So we've got a patient here, and as usual, he's going to the hospital to either get treatment or diagnosis. So he's paying for that treatment. Potentially, he's going to be refunded by his healthcare provider, partly, fully. It depends on the countries, depends on the policies. That's the traditional use case at the moment. And as we've said before, what happens at the moment is that the hospital will keep this data in a private database. Most likely they will not use it, because they're not allowed to do it at the moment, and they might not even be able to share it within cross-institutional studies. I take part in, for example, in a project where we work with different hospitals in the UK, and even sharing data across hospitals just for research purposes, and even with the consent of the patients, is challenging with regard to the legal framework. So this is something tricky already. Now imagine something. Imagine that we give a button to the patient, allowing him to decide whether he actually wants his data to be shared in a public database, for example, or he doesn't want them to be shared at all, and under what kind of circumstances. So there's little padlocks next to each of these databases. That means that even if the patient decides to share his data, he still wants his privacy to be enforced all the way through during the usage of his data. Now, what could we do with that? Well, we could incentivize this patient by providing him a sum of money directly to him or to his healthcare provider, for example, for sharing this data. Because most likely this data will be beneficial to other patients and to the healthcare system in general. So here we're speaking about a potential technology that could revolutionize the way we're paying for healthcare, not only in Europe, but in the world. And I think that's a major concern for everyone with the way we're going with this healthcare system, the aging population. We need to find new ways to pay for healthcare and for quality healthcare. What I mean by quality healthcare is that at the other end of the world, a data scientist that's an expert building artificial intelligence could benefit from data that is never seen before, because this data were left untapped in silos because they were private, so we don't want to share them. Now, if we give him access to data that remain private all the way through, and that still allow him to improve his artificial intelligence, well, of course he's going to pay for this data, because that's a very valuable piece of information for him. But on the other hand, he's injecting a lot of value in the system, because potentially he's going to be able to develop new artificial intelligences that's going to allow us to provide better diagnosis for the same patient or for the one next to him. So all what that describes is a new kind of a decentralized economy, decentralized marketplaces that benefit from both blockchain technologies but also security and secure computing technologies in order to create a win-win situation for everyone, for the healthcare policymakers, for the patients, for the hospitals, and for the industry players, both on the tech and the healthcare side. That sounds great. And actually, that's enabled by a very nice diagram that I saw from Heather, that you've seen before. Why can we do that? We can do that because we've got the convergence of all these technologies. So I'm not going to spend too much time on that one because you've seen it before. However, there's still a lot of challenges around that. We've heard that before in the panel as well. No one wants to keep the data, right? That data is toxic because, of course, you can make a lot out of it. But if you're responsible for managing it, then it's a huge burden on you and your company, right? So who's storing the data and who's giving access to the data is a big challenge. How do we incentivize users to take part in this ecosystem is a big challenge as well. And of course, blockchain and all these tokenization processes can give us some answers in this direction. And then there's also all the byproducts of what we're building with that. Are we sure that we're not leaking information that we would not be happy with revealing, even though we think we're maintaining the privacy here? I'm not going to speak about all of them for the sake of time, because I know I'm the last barrier between you and lunch. So I'm going to try to remain focused on a few of them. I'm mostly going to dive into secure computation. Secure computation is the field of technology, the field of techniques, mostly drawing from cryptography, that aims at running applications, so a given piece of computation, on data that remain encrypted, one way or another. Okay? So the idea is that at the moment in order to process something, in most of the cases what we do is that we reveal the data to a third party. So sometimes this data is encrypted when it's stored, it's encrypted when it's transferred to another party, but then this party needs to decrypt this data. And we see a lot of models where blockchain is used to control the access to the data. So as a way to permission data access, which is great. But if you just stick to that level, you're basically doing nothing. Because once you give access to somebody, you might just as well revoke this access 3 months later. If the third party has seen the data in plain text, the data is lost, right? Even if the third party is very good-willing and is not trying to cheat on you and trying to sell your data afterward, he might still be under attack, as we've seen before in other industries as well. It's going to come for healthcare. So there is a risk for a third party to see your data in plain text. What these technologies are providing is a framework to allow third parties to run computation on private data without having to see them in plain text, right? The first three of them are kind of like in a simple form, answering the same question. So how do you run these secure computations? And I'm going to address them in a practical point of view. So what's the most tractable at the moment? So from the least tractable to the most tractable, but we see that they all have use cases. Homomorphic encryption, that's the holy grail of cryptography, all right? That's something that's been worked on for years, like for decades now. That has seen like a major improvement in the 2000s by a guy called Craig Gentry and his PhD. And that's the idea that you can design a function f, any kind of mathematical function you can think about, right? and if you apply this function on a piece of data, on a message, well, you obtain the result of this function, right? What homomorphic encryption is trying to do is that now if you encrypt this same piece of data, and if you have a way to encrypt this function as well, well, applying the encrypted version of this function to your piece of data will give you an encrypted result. And by crypto magic, when you decrypt the result, it's going to be the same as if you had applied the function to the plain text data, right? So that's literally the holy grail of what we're trying to do. What kind of use cases will that enable? So if you've ever used any kind of, there's already lots of machine learning APIs available, like Amazon, Azure, all the big cloud providers. They let you, for example, even the apps in your smartphones, they let you upload an image, for example, and apply a filter on it, or do some image recognition, or do some automatic translation on a piece of text. And what you do in all these cases is like you take your private data, potentially, and you send it to a cloud, to a compute cluster in the cloud. At the moment, you're doing it in plain text. What homomorphic encryption will allow you to do, and what homomorphic encryption allows you to do, is to encrypt this data. So you're the one who has the key. And as we know in blockchain and all cryptography, the one who controls the key controls the data. All right? If you lose your key, that's not. So you keep this key for yourself, and you encrypt this image of your dog. You send it to the cloud, and the cloud has homomorphic encryption compliant application, in this case, an artificial intelligence model. And it's able to run, to apply this model on encrypted data. So technically, it doesn't even know what it's doing. It receives a blob of data, and it runs it without really knowing what it's doing, and sends you back an encrypted prediction. You decrypt it, and you get a prediction that says the image you sent is actually a dog. Fair enough. All the way through, your data remain encrypted. When you stored it for yourself, when you transferred it, it was still encrypted, and when you processed it, it was still encrypted. Yes?
I'm going to throw another one out there. Isn't the problem, though, with encryption that, there is not an encryption standard out there that cannot be broken yet? So, if you're using encryption in a blockchain environment, that is a major issue.
There's an answer at the end of the room.
I mean, there definitely are ones that haven't been broken yet, obviously.
Well, I'm just going to say, there's encryption, there's a hashing, and I think it's a discussion about an intermix, and I don't think you can just rely on encryption, basically, right?
You can, but what cryptographers say is that everything is going to be broken eventually. It could take 10 years, it could take 100 years, everything is going to be broken eventually, right? But what we mean by that is that it's about doing the best that you can nowadays with the technologies you have, right? Of course, if you pick a cipher that's already known to be broken or known to be, for example, in the context of the modern technologies, non-quantum resistant, so non-resistant to the future quantum computers, you shoot yourself in the foot, right? So you want to pick the best technologies available at the moment that are future-proof to the best of our knowledge.
Could I just add a quick comment
Yeah.
to that? Modularity of the encryption function in blockchain is a really key future-proofing idea.
Yeah. Well, that's the kind of discussions we're having anyway. So, and that's where standardization bodies are important as well. Of course, it's about assessing like the risks of all of these things. Yeah.
A common practice in encryption is to add salt to the encrypted text or the encrypted data. Do you know if homomorphic encryption operations are possible if you solve the data?
If you solve the data, good question. I think it depends on the scheme you're using. So you mean like if you solve the data in order not to have the same encryption for
a genomic sequence.
Yeah.
I solve the genomic sequence.
Yeah.
I apply operation on genomic sequence. Would the result of this operation be relevant as an outcome?
So that would imply that the scheme, so the cryptographic technique that you use for homomorphic encryption, is aware of these solved mechanisms, right? So I'm not going to go into details of all the schemes that are available today. They all have different flavors and different features that can be useful for one thing or another. I guess if you were to go for genetic data, for example, that's what you would like to do. So yeah, most likely you would have a scheme that's able to understand these kind of things. If you want really to go quickly into the details, the way it works is that the cipher is able to run operations. It generates some noise around the results, but not enough to prevent you from decrypting the results. So that's kind of like the same idea behind the scenes.
Would this scenario also be possible with public and private cryptography, so that you can have a different key in the first and the third step when you different persons?
So you'd have-
decrypting it?
Yeah, but that'd be a problem.
Would it be
Because
possible?
it would be possible. You can do it already with these kind of things. You can encrypt, then you can encrypt with the public key of the cloud, for example, send it the data, it will decrypt it in a private environment and run the model on the decrypted data. But then you have risks that the data is being leaked or lost or hacked in the process. So what we want is to make sure that it stays encrypted all the way through.
Yeah, but I mean, can you get the result with a different decryption key? For example, the first step are people who upload their medical data.
Yeah.
And the third step are researchers who use that medical data, who are different people. Because in this scenario, they would have to trust the people, once they decrypt the result, that they share the correct data with the researchers.
Right, okay, I see what you mean. Yeah, so this scenario that I'm describing here is very much peer-to-peer. So it's not involving like multiple institutions. That's an active topic of research for homomorphic encryption. How do you use multi-keys in homomorphic encryption? That could answer your problem. But yeah, this scenario is very much focused on like providing the benefits of artificial intelligence or any kind of advanced processing technologies to an individual that owns private data. Okay, so a lot of challenges here. Well, first of all, encrypted data is always larger than the plain text is encrypted. So if you start having very large pieces of data, it means you can have huge ciphertext. So in some settings it might be challenging. The main problem at the moment is probably the significant overhead that's involved by these technologies in terms of both compute and memory when we're trying to apply them to very complex computations. So in terms of AI, for example, there's a very widespread model for object recognition that's called MobileNet. It's meant to, as its name suggests, it's meant to run on your smartphones, IoT devices, all these kind of things. If you turn it into a homomorphic way, the last experiments that we've been running a few months ago was basically requiring 150 gigs of memory just for this model. So we're not very mobile anymore, right? I don't think any of us has 150 gigs of memory in their phone. So that's the challenges in terms of compute. Some of the state-of-the-art pieces of technologies there run basically at the speed of the computers we had in the 80s, if not less sometimes. But again, this is actively researched, and there's lots of academics and companies working in there, and there might be like significant breakthroughs in the coming months and years. So definitely not a roadblock forever. But that's complex cryptography. So we're lucky because like there's very talented people working on that, but there's few of them. So that's the roadblock as well. A bit more tractable and something that's been used for about 20, 30 years in production as well. Something called secure multiplayer computation. So now we're not really considering these peer-to-peer setting anymore. We are, for example, let's say we would like to know the average salary of people in this room, right? That's sensitive data. No one really wants to discuss the salary, it's always annoying. But we would like to have an average in the room. So how do we do that? Well, for each of us in the room, for example, we split our salary in shares. So if we are 80 of us, we split our salaries in 80 shares. These shares are random as long as they add up to the initial value. Okay, that's the concept. We give one of the shares to each of the other persons in the room. So each of us is still with 80 shares. You have one that is yours and one from all the other persons in the room. Well, the cool thing is you can add these shares together, right? Yours and all the others that are not yours, and they will add up to the result we're interested in, to the sum of the salaries. So then you're just left with, you have a data that you didn't have before. You just have to divide it by the number of people that were present in the room. No one revealed any kind of sensitive information, but we all learned a new piece of information from the group, right? So that's the kind of ideas that people are using as well. Again, oh, sorry. Question, someone? Oh, sorry.
So if I divide my annual salary
Yeah.
in 80 parts,
Yeah.
I give it to my neighbor.
Yeah.
She will know exactly my salary, right? By multiplying it by 8.
No. You just give her 1 out of 80s.
Yes. And she will multiply by 8 because she's doing the same. So she knows my salary.
Parts are not equal. Just 80
They're-
parts.
they're random out.
So they're random parts.
Okay, random.
Yeah. Yeah.
Not an equal split.
Pardon?
Not an equal split on my salary.
No, of course not. No.
Sorry.
No worries. So that works extremely well when you're doing additions. It's very simple, right? Now when you want to do machine learning models, they're basically made of additions and multiplications. Okay, so multiplications with constants, pretty easy. That's basically a sum that you repeat over and over again. So we know we can do sums very easily. So multiplications with public constants, super easy. Now if we want to multiply together private shares, then that becomes tricky. Okay, that's where the limits of these technologies are coming in. And it's something that's very important here, and that's, I think, very well highlighted by these technologies. For everything you're doing in secure computing, there's no free lunch. You can't have the privacy and the performance and the ease of use and everything, all right? So what happens most of the time is that you end up re-expressing your problem in a different way. So you've got to accommodate for what the framework allows you to do and what the framework is not good at doing. And in the case of machine learning models, for example, that means that what you use in the regular setting, well, you often have to adapt it for operations that are not equivalent, but very, very close mathematically in terms of results, but that are much easier to compute in this framework. All right, so you end up having approximations of functions. You end up replacing some of the layers in a deep neural network, for example, that end up allowing you to process what you want while keeping these private settings. So the take-home message here is that it's not very easy to translate something in the same way from the plain text to the encrypted world. Last, one of the threes, and the one that's probably the most in use, especially in the blockchain world actually. Trusted execution environments, TEs. The piece of technology is a hardware piece of technology this time. The two previous ones were mostly software technologies. This one is a hardware-based technology. The way it works is that your processor, all the processors we have in our phones and laptops these days, the modern ones, they pretty much all have these piece of technologies, which is a way for the processor to create a very small, kind of like 100 megabytes of memory, a very small area in the memory of the computer that is encrypted by the processor itself. So what that means is that even if you have any kind of administrative privilege on the machine, you can be the administrator of the cloud, you can be whoever you want, the processor will set this cryptography. So even the most privileged users on the machine will not be able to see what's happening in this very small zone. All right? And what you can do in this zone is send data that you've encrypted beforehand and that will be only visible and decrypted within this very secure area of the machine. Okay. So you get the same kind of benefits and use cases that you have for homomorphic encryption, but you get it from the hardware. The good thing is it's fairly easy to use compared to other declinations, right? You can pretty much take an existing piece of code or an application and port it very quickly to support these kind of environments. The tooling is there, or at least it's more production ready than the other ones, and it's in terms of performances, either directly or combined with other tricks that are actually researched as well. It's probably one of the most scalable solutions we have. The most popular solutions these days, mostly Intel SGX, which is the one being championed by a lot of people in the Ethereum community. You've got a company called iExec, for example, that's very good at building around these pieces of technologies. But it still has challenges, still has problems, right? Again, no free lunch. So limited amount of memory, 100 megabytes, not much if you're doing very fancy things. Still another head when you process things. And what I think is the most important, especially when we're talking, we were discussing trust in the systems before. Well, here you put a lot of faith in the vendors, right? So you believe, you trust the vendor to provide good enough cryptography for you to encrypt your data on these pieces of the hardware. You trust them not to have inserted backdoors in these processes. So it's a very good way to, I think, change the ways we're processing things. So as a first step on the ladder towards more privacy in depth in our solutions, but not what we should aim for as a community, I think. Yeah.
How do you import your keys in trusted environments?
So you don't really import your keys. The environment has its own key. That's where the vendor puts you put the trust in the vendor. So the key is baked in the chip, basically. And you have a way to request the public key from the enclave to encrypt your data, so that it's only being decrypted within the enclave itself.
How practical are side channel attacks? Do you see it as a major?
There are a lot of side channel attacks on that one.
Is it problematic for realization?
It is problematic. It is problematic in two ways, because side channel attacks can happen on these hardwares, and the thing is, it's much harder to upgrade a piece of hardware than a piece of software. So if you find a security problem in a software, you can easily update it. For hardware, if it's not something that you can patch with a firmware, for example, if it's something that's really bound to the hardware itself, it means you can have a lot of machines compromised and not easily upgradable. So yes, side channel attacks big issue on that one. Lots of research papers targeting both AMD, ACD, and Intel SGX with regards to these side channel attacks. All good? Okay, so that's pretty much it for the secure config capabilities we have available. Now, how do we get users to take part in these things? And I think that was a question before, like somebody asked, how do you get the users to? Are they happy to share their data? Even in the gamified process, are they happy of doing it? Well, the good thing with blockchain is that we have this ability to create token economics around all these pieces of technologies to incentivize users either financially or with a gamified approach. Yes?
I'm sorry to do this, but the financial incentive about users rewarding to share data is actually something that is also highly ethically problematic. For example, if you are a rich white male and with private health insurance, you don't have to share your data, but everybody else does. So as an industry, as we look at this issue, the idea of incentivizing people to share their data is actually not only an economic issue, but a class and gender one. And when you apply that in healthcare, you start to run into some massive, serious, cannot overcome issues. You're not
That's very true. That's very true. So that's why, again.
Let me give
Yep, go ahead.
Let me give you a counter there. It's your data. You own the data. So who is going to limit you to do with stuff you own what you want to do with
But
it?
if we can't get it, I'll give you a perfect example, the difference between private and public healthcare, even in Germany.
Yeah.
And I don't wanna knock the German system because it's also much better than the American system, for example. However, if you're in an environment where you are being incentivized economically to share your data by your insurance company, and for example, let's say there's an error and a problem downstream, how do you correct that? You should not be incentivized with your health to earn money to get better health. That's like the absolute antithesis of comprehensive healthcare, no matter how much money you have. So if I'm being incentivized to share my data with money, that means who is that going to be most attractive to? People without money, people who are supposed to be covered comprehensively. That is what we're running into right there.
You need
People
to,
think it's okay to sell your data.
but you need to have an incentive for people to share the data.
Well, why is
And
that
the
not?
easiest incentive you can give there is either like you do it abstract and say like you will have like better health in the future, or that other people will have better health in the future, and you're profiting from people who did share the data in the past, but that's altruistic. Or you do it monetary wise, which is like universal.
I'm sorry. I think that is a very, very dangerous and slippery slope for any policymaker to even consider in healthcare. You do not economically consider, you do not economically incentivize, I'm gonna waive my privacy at X because I'm gonna get paid.
No, I think that's where all the token mechanisms are helping us actually, because like you can see it as financial rewards, but you can also design it as another gamified process, for example. So if you're not happy with financial rewards, it can definitely be inserted into another system that gives you other benefits. It doesn't have to be financial.
What I would like to propose you is that we have a dedicated session on that in the afternoon, so we can talk about the ethics and the implications of it. In the afternoon, we have the opportunity to talk more about the technical aspects, so if we can more focus on that aspect right now and then move on afterwards, that would be great. Thanks.
Of course, thank you.
So just
Yeah.
just relating to incentivizing users, I think that is the counterpart of this. However, let's say we assume we should incentivize in some form.
Yeah.
The counterpart is that you could also get incorrect or invalid data in response to incentive, and I think that's a challenge to work through
That is very true.
as well. And then I would add another counterpart is the sort of selection bias.
Yeah.
As well.
That's hopefully that's something we can prevent from a technological point of view. And that's very interesting actually, because what I meant with this slide is that for me the best example of how that could take place in a relatively short term is being implemented in something that we call federated learning. And that's actually one of the main problems of federated learning. So the main problem is actually, yes, if somebody contributes wrong data, then of course you get garbage in the output, right? So how do you prevent, how do you detect these kind of contributions? And it's even more challenging if you still want to maintain the privacy guarantees. So there's a lot of work to do in these directions, but very good more. Federated learning is actually something that you're familiar with, I'm sure. Maybe even without knowing it. Who's got an Android phone around there? A few of them? Lots of iPhones. Oh god, I don't know iPhone very well. Did you notice something recently that your keyboard, if you're using the Google keyboard, was starting to suggest emojis at the end of sentences? Or
iPhone does it as well.
iPhone does it as well. So I don't know how iPhone does it, I know how Android is doing it. So that's one of the main and first like major scale applications of federated learning that Google came up with. So what they're doing is that they've got a prediction model for a general one that they baked themselves for what is going to be the next word in your sentence, for example, or what does this sentence mean, and what is the right emoji to put next to this sentence. So that's something that you can build in a traditional machine learning way. Now what they want to do is they want to improve it based on your inputs, right? But they want to do it in a privacy preserving way. So if they were to take what you type on your keyboard and bring it on their cloud, that'd be awful. So we don't want to do that. On the other hand, what they want to do, and what they're doing, is they can send their model to your phone, right? And with the model on your phone and the data, your own data on your phone as well, you can improve the AI a little bit. You can train a little bit with your own piece of data and just send back the result to Google. So you're not sending your data anymore. You just send a little improvement to the model that you've been computing with your own data. Now, if you're doing that across the whole swarm of people owning Android devices, well, first of all, because you're aggregating this data, these updates together, that are not even the actual data, but really updates, you blind them in the upgrade. So you maintain the privacy by the sheer amount of data that you're integrating in the model, right? And when you send it back, these aggregations, you can obtain an improved model that can be then sent back to the users for an improved experience on their phones, while maintaining their privacy all the way through. So that's the idea behind federated learning, and that's how it's being used. There was a point in the panel saying, now, how do I know who's accessing this data, who's accessing this piece of AI, for example? And that's, I think, where blockchain have a role to play at the interaction between federated learning and the users. So we can imagine that blockchain can be used to orchestrate the interactions between data providers, us, and who's accessing all data, right? So you can use it to build an audit trail that would record not only what data is being accessed by whom, but also what kind of steps have been taken to improve the artificial intelligence model. And that's actually a piece of design that we are trying to come up with at ConsenSys Health. One of the first iteration of that's Verov's sketch of what could be these kind of integrations. Well, you can imagine that somebody owns a model, we register it to a smart contract that would play an orchestrator. And what this smart contract would do is then register what we call data workers. So elements in the network that own a specific piece of data that could be valuable for improving this model. Well, by using encryptions that we have in the Ethereum ecosystem, you could send this data. You could use these data workers that have data, send them the model, okay, all the way while registering. Is that a question? No, sorry, I thought you were that. Okay. You can run a training round on these data that remain on the data worker, and you can encrypt back the output, right? The output of these new training rounds can be stored on any kind of distributed storage that you want. Can be IPFS, can be Swarm, can be anything that you think about. Can be Filecoin. Actually, the logo here looks very much like Filecoin. And you can aggregate that in a secure fashion, still using Ethereum-based encryptions all the way through. Okay. And what I think is very important in this context is that we're not only using blockchain as a way to reimburse or reward workers for this contribution. That's a very optional piece of the design. What's more important is that we're using blockchain to give access or not to the data to a specific model owner. So as a data owner, you can decide that this or this person will not have access to your data, whatever they're doing with it. Or you can define very fine-grained permission policies to this data. And you can also make sure that these workers and these trading rounds are all logged in a privacy-preserving fashion in the blockchain, so they can be audited later on, in case there's a problem, in case we want to change the permissions. Everything will be kept in these immutable ledgers that we have at the moment. A few references on there, Google's references, our references, feedback always welcome. And a quick summary of that. So I think, again, the take-home message is that all these technologies can only work if they are combined together. All right, they do provide benefits on their own, but I don't see their full potential being used in a standalone fashion. Right, so we want them to be combined together to make the most out of them and to make the most out of data and out of our infrastructures. And they actually solve, some of them solve different problems. So we've seen a lot in this origin of input privacy, which is guaranteeing the privacy of your own data. We've seen a little bit on how blockchains and DLTs in general could tackle policy enforcements in the realm of federated learning, for example. One thing we did not discuss is how do you address the privacy of the output, because that's something that's very challenging as well when you're building artificial intelligence models, is that you can make sure that you're guaranteeing the privacy of something, of the inputs, all the way through. But after all, an artificial intelligence is supposed to learn on the data it's being fed with. So if it was not learning, it would not be a very good artificial intelligence. So it means there's some form of representation of your data, of the information you've provided, that's been captured within these models. Right? So how do we guarantee that the information that is being captured is not leaking any kind of sensitive information about you? And that's out of the scope of this talk, unfortunately, but if you want to look into technologies like differential privacies, that's the kind of things that you can apply on top of all these other technologies to have the full view. Yes, thank you very much.
How would you define the state of all these privacy-preserving technologies? Because the interaction comes when certain advancements outside and beyond the research stage has been.
You mean like what's ready, what's not ready?
I mean, if you had to implement them combined in a combined way, which ones would be reliable and trustable?
So federated learning, I would be confident using it. Mostly because that's been proved to be working, both in academia and in production, as we've seen in Google. There's always the risk that you're not going to have enough data to make it work the way you want. So I would definitely be interested to see it being applied at the very wide institutional level to kind of like reproduce the scale of data that large companies have in hand. That would be very interesting. As I said, like anything around trusted enclaves, that you've got things running on them at the moment. So that's again something that is not probably desired for the long-term future, but that you can definitely harness as of today. Differential privacy being used at the moment as well. Apple and Uber are big on that. They are very very bullish. It's quite interesting actually, because like we've had quite a lot of pushbacks on the big American companies, but they're not as bad as we might think. Of course, they're not perfect, but they are pushing for some of these technologies as well. So it could be that they're feeling the tide and they are willing to engage into more privacy-preserving fashions, hopefully. Yeah.
In light of the what's accessible and usable now, could you speak a little bit to defining zero-knowledge proofs and how they're being used in production today?
Yeah. So I deliberately avoided zero-knowledge proofs in the talk because they're a bit challenging. And so zero-knowledge proofs, for those who don't know, that's a concept that allows you to prove that you know an information without revealing this information. It's a bit conceptual, but that's something that's very popular in the blockchain world today because it has many use cases. It can allow you to compress a lot of information to scale blockchains. But in our case, we're more interested in the applications to what we call verifiable computing. So another challenge that I didn't raise during this presentation is that even though you keep the privacy, when you apply a model, when you apply an application on input data, how do you prove that the person that's applying this model on your data is actually doing what it's pretending to be. Because actually, it's running on encrypted data that it should not see, and it's giving you a result, right? How do you assess that this result is correct? It's actually very simple when you, for example, provide image recognition, any form of artificial intelligence-based outcomes to degrade a little bit the model. Why would you do that? Well, if you're a big company, you don't have any interest in doing that, right? If you're Amazon, if you're Microsoft, you're running machine learning as a service, people expect you to run the application that you're claiming to run. And if you're not, and if somebody finds out one day, your reputation is destroyed, right? So your capital in this case is the trust that the customers put in your applications. Now, if we move into a fully decentralized world, when it's not only Microsoft and Amazon running services, but it's like anonymous individuals on decentralized networks. Well, the only incentive that they have is financial, technically. They would provide you a service, they would give you compute time on their machine in exchange for financial compensation. So their direct incentive is to run as many computations as they can, right? So if they can degrade a little bit the model without you really noticing the difference in the output, but it still would be a difference, so that they can run one prediction more in the same time frame, well, they're winning, right? Because you still get your prediction, you don't really notice it's different, but it's not really what you paid for initially. So that's where zero-knowledge proofs, hopefully, and other kind of technologies as well, could address these challenges in what we call verifiable computing.
Maybe one last question, if there is any.
Is that the issue of data privacy not only relevant with data sets which include an individual name? And isn't it the case that most treatments and services which are offered under the condition that you have to provide the data anonymously to the provider of the service and the treatment? So all the data are anyway sourced from the industry, and the few cases where really your name has to be attached to your data set, of course, if you are ill, you give it away. So
is the question like, why do we need all that? Because we're already doing it with anonymization. Yeah. So anonymization has been proved to be broken, unfortunately. There's been like a few attacks on re-identifying individuals using combined data sets. So the thing is that the problem is not about what a single piece of data is leaking away. It's how do I combine these data with another data that no one was thinking about previously, for example. The most iconic example was the Netflix prize in the 2000s as well, where Netflix released a data set of what their users had been watching in order for data scientists to provide better models to predict what their viewers would be most interested in watching. Well, people have managed to cross-correlate the entries in this dataset with comments on IMDb, and they've been able to re-identify the Netflix users in this dataset with a very high accuracy. So anonymization, I think we should completely take it out of the question nowadays. That's been used for ages, and we should stop doing it. Because even though we should not have like perfect faith into cryptography, because everything can be broken one day, I think anonymization has been broken today and yesterday, so we're not even speaking tomorrow.
Also, the second use case is not only anonymization, it's if you have full encryption chain with everything in there, then you actually don't give the plain data out of the hand, as it means if you have a sales model, you can resell it more often.
So there's a friend of mine coined this term that I'm reusing without signing him anymore, which is called AI for rent, and you can say data for rent as well. So that's exactly that. If you sell or data applications models in plain text, what's my incentive to buy it again, right? I've sourced your data. Maybe I'm going to create a second-hand market and resell it to somebody else, but I'm not going to buy it again from you. Whereas if I'm buying queries from you, private queries, then I might have to buy it again and again. So technically, you're more renting your data and renting your models away rather than selling them, and that's probably a more interesting business model for small individuals.
Thank you very much.